Good afternoon, everyone. My name is Alex Hankin, and along with my colleague Dave Werner, we are going to present the research we have been working on with our group at Tufts, along with partners at Google and Intel, to develop tools to study advanced hotspots. We present HotGauge, a methodology for characterizing advanced hotspots in modern and next generation processors. While thermal hotspots have been around for years, we define advanced hotspots as those which are of a higher severity, specifically those which will require throttling and non-trivial performance degradation to mitigate. These advanced hotspots have emerged suddenly, but not surprisingly. With each new process generation, additional logic is crammed into space saved from smaller transistors to create ever-increasing post-Dennard power densities on the die. The problem can no longer be dealt with using traditional methods like DBFS without unacceptable performance degradation. It is critical for the architecture community to develop more intentional and intelligent hotspot mitigation techniques. Here we are showing an example hotspot during a simulation of a 7-nanometer client processor similar to an Intel Skylake. What we can observe is that hot functional units exceed 120 degrees Celsius, while logic within 200 microns remains more than 30 degrees cooler. Additionally, the speed at which these temperature deltas are rising is fast, and it's increasing with each process node. Here, we are showing the distribution of temperature deltas of the core over 200 microsecond intervals. Each distribution is a slice in time and color-coded across time to help visualization. What we can observe is that temperature deltas are higher in 7 nanometers than in 14 nanometers. For example, for 14 nanometer, the first slice has a peak at around 2, while 7 nanometer has a peak at around 4. This means the chip heats up more in the same amount of time, which will result in faster hotspots. Furthermore, we can observe that the distribution of temperature deltas within 200 microseconds is significantly wider in 7 nanometer than in 14 nanometer. This means that there is an increased potential for local temperature deltas like those shown on the previous slide. The advanced hotspots we are seeing are a direct result of on-chip power density. The localization, application dependence, and exponential increase of power density since the end of Dennard scaling has had a problematic effect on thermals. Standard thermal sensors and control mechanisms simply won't work anymore. The community needs targeted architecture level mitigation techniques that can respond in a fine-grained and quick manner. To develop such techniques, the community needs the appropriate metrics, models, and methods for simulating advanced hotspots. To address this need, we present HotGauge, a methodology for simulating advanced hotspots in modern and next generation CPUs. HotGauge consists of two main steps: performance, power, and thermal co-simulation, as well as hotspot characterization. First, performance, power, and thermal simulation is needed to collect the necessary raw data for identifying hotspots. This requires inputs of all system models, performance, power, and thermal, as well as the workloads to be run. This also requires floor planning for the thermal model and an interval for how often data should be collected during simulation. Next, once transient data for thermal simulation has been collected, hotspots can be detected and characterized. First, a definition of a hotspot is needed, then a way of detecting and classifying the severity so that different floor plans or mitigation methods can be compared. For the hotspot definition we developed, our goal was to capture all aspects which will cause performance loss or reliability problems. For example, absolute temperature negatively affects reliability and in fact affects transistors and interconnect differently. Large nearby temperature difference, or MLTD, on the other hand, affects performance by impacting the safe clock timing margin. The detection algorithm is described on the right. First, at each time step, we collect the local temperature maxima on the IC. Then, for each, we look at a neighborhood of temperatures based on some radius and evaluate the temperature differences between the center temperature and all neighbors. Localized temperature differentials arise due to 1, the different ways in which temperature affects transistors versus interconnect, and 2, because of the difference in activity between neighboring transistors, subunits, or functional units, depending on the granularity of interest. After identifying all hotspots, we compute the severity of the hotspots. We developed a severity metric which produces a value between 0 and 1, indicating the severity of the hotspot based on our definition. A value of 0 indicates conditions where there are no hotspot-related issues, and a value of 1 indicates conditions where the chip will experience immediate errors, crashes, or permanent damage. We further define that the value should be 0.5 under conditions where immediate mitigation steps are required in order to avoid hotspots. The severity metric is a function of multiple sigmoid functions which have the following form. This parameterized sigmoid function was chosen because it enables smooth interpolation between low and high values and has other parameters that can be adapted as needed in order to match desired constraints. The first term in the severity equation, sigma df, defines where device failure is imminent based solely on the temperature of the IC. The second term in our metric is the product of sigma m and sigma t, which are the marginal contributions of MLTD and absolute temperature for timing issues. It is necessary to consider both MLTD and absolute temperature simultaneously because of the nonlinear relationship between timing and temperature, which happens due to the opposite effects on timing that temperature has on logical circuits relative to global interconnects. To demonstrate the utility of HotGauge, we modeled a well-known processor similar to an Intel Skylake and used a set of open source performance, power, and thermal simulators along with our hotspot definition, detection algorithm, and severity metric. Here are some of the details of the models we used. And I would like to note that all of the details are in the paper. Some key things to point out, we looked at 14 nanometers, 10 nanometers, and 7 nanometer process nodes, and we also ran the processor at turbo boost, a 5 gigahertz frequency. Now my colleague Dave will discuss some of the results and some of the conclusions we derived from them.
Thanks, Alex. So as Alex mentioned, my name's Dave Werner, and I'm going to be presenting some of the results and analyses that we've done using the HotGauge framework. In the coming slides, I'm going to primarily try to do three things. One is to show how we use the framework to quantify how bad the problem currently is, show how much worse the problem is going to get in the next generation of processors, and then lastly, I'm going to show some of the results of how HotGauge can be used to evaluate mitigation techniques and compare their effectiveness. So for full details, I would encourage anyone to look at the full version of the paper, but I'm going to show a sampling of the data that's found in the paper here in this presentation. So first, I want to demonstrate how MLTD changes with tech node. So here you'll see two plots. On the left is the 14 nanometer node, and on the right is the newer 7 nanometer node. And what I've plotted here is the MLTD in different cores across time using the GoBMK benchmark. And the two main trends that I want to point out here are one, that in the 7 nanometer node, the MLTD is significantly higher, which means that the hotspot problem is worse. And secondly, that the variation in MLTD from core to core, meaning if GoBMKs were on core 0 or core 1 or core 2, and etc., the MLTD varies more. So the MLTD is actually more dependent on what core you run in the newer node than it was in the older node, which means that the problem of mitigating hotspots is not only worse in 7 nanometers, but it's also more difficult because there's secondary factors that will play into it as well. Next, I want us to look at the summary data for the time until hotspot. So for this analysis, we ran the workload shown here on the x-axis, and what we did is we ran at the turbo boost frequency, as Alex mentioned, and we measured how long it took for a hotspot to develop under that benchmark. And the things that I want to point out here are, one, that from benchmark to benchmark, there's a huge range of time until hotspot. So here we see a log scale. So some workloads have a hotspot develop hundreds of times quicker than other workloads. So this means that hotspot behavior is very dependent on the workload being run. And a secondary trend that I want to point out here is that for some workloads like GoBMK, core placement is actually pretty significant as well. In this case, we see if GoBMK is run on a certain core, it develops a hotspot 100 times faster than if it's run on another core. And that's simply due to differences in core orientation and what surrounding elements there are to that core. Next, I want to look at where hotspots occur. So what we did is we aggregated where all the hotspots occur across all of our workloads, and we've shown that as a heat map here. In this case, we're zooming in on core 1, so we're looking at a single core. So within that core, where do hotspots occur? And what you'll see here is that there are a few key areas, as I'm showing here, where there are most of the hotspots occurring, given our workload set. And the red dots are where some hotspots occur, but not as frequently as shown in yellow and blue. So while there are a few key areas that we can potentially target to mitigate hotspots, what this shows is that there are still hotspots that occur infrequently in other locations. So any mitigation technique that we develop needs to, one, target these problematic areas, but two, needs to also work for the other areas not targeted by those techniques. And so what we argue here is that the mitigation techniques need to be runtime and dynamic so that they can mitigate all of these hotspots rather than just a few select ones of them. So as the first case study that I'm going to present here, we did a single unit mitigation. So the goal here was to identify the problematic units as shown in the previous slide and decrease the hotspot severity in those units themselves. And as a baseline goal, we aim to make the 7 nanometer unit behave no worse than the 14 nanometer unit in terms of hotspot severity. And our justification for this is simply that the 14 nanometer parts are out in the wild and the hotspot problem is manageable in them. So if we can make the 7 nanometer unit no worse than 14, we've effectively mitigated the hotspot problem of that unit. And the method that we've chosen to evaluate this mitigation technique is simply adding white space around the unit, scaling the area up, thereby decreasing power density, and show the results on the next slide. So in this case, we're scaling the area of the floating point instruction window. On the left, you'll see a run of GCC. On the right, you'll see a run of milc. I want to focus in on GCC for the time being. So each one of these series is a certain node at a certain scale factor. So the baseline 14 nanometer node is shown in blue here. And the others are the 7 nanometer processor with the floating point instruction window scaled by some factor from 1x all the way up to 10x. And so what you'll see here is that we were able to reduce the hotspot severity in the floating point instruction window by scaling the area up. But even when we made it 10 times as large as the baseline, it was not as good as it was in 14 nanometer. So what that means is that while we did reduce the hotspot severity, targeting this single unit did not fix the problem, as there's still high hotspot severity in the floating point instruction window simply because of the other surrounding units contributing to its temperature. On the right, you'll see milc running instead of GCC, and in this case what we see is that not only is the hotspot severity lower, significantly more low in 14 nanometer, the effectiveness of scaling the floating point instruction window is much less than it was for GCC. So for milc, scaling the floating point instruction window was not an effective mitigation technique. Now, just to show you that it's not milc itself that's the problem, I've shown scaling different units for milc here. On the left is scaling the floating point instruction window that we talked about on the previous slide, and on the right, instead, we're scaling the register files. And as you can tell, when we scale the register files, we have a much larger decrease in the hotspot severity, which is what we're aiming to do, our mitigation technique. But what we see again is that the 14 nanometer baseline is still way out of reach of this mitigation technique. So what we need is not only these targeted mitigation techniques, but something that is going to simultaneously target and mitigate hotspots in the surrounding units as well. Now that we've seen a zoomed in version of the data, I want to zoom out and look at the overall results. So here we're just showing the effect of scaling another problem unit, the register access tables, for all of these workloads. And what I've shown here on the Y scale is the peak hotspot severity. This left set of data points is for the 14 nanometer baseline. And the first thing that I want to point out is that even for the 14 nanometer baseline, the hotspot severity reaches 1 in nearly half of our workloads, which means that the hotspot problem was already bad. For the remaining workloads, it peaks below a value of 1, but still above a value of 0.5, which means that for all of these workloads, some level of mitigation would be necessary to prevent the chip from overheating and damaging or destroying itself. In comparison, the 7 nanometer nodes shown here in the middle, nearly all of the workloads reach a hotspot severity of 1, which means that the problem was bad and now it's way worse. And then on the right, what I've shown is the results of the 7 nanometer processor with a register access table that is scaled by a factor of 10x. And what we see is that for some workloads, it does indeed reduce the hotspot severity, but its effectiveness varies across workload to workload. So while scaling the register access tables did help, it did not help in all cases. So dynamic techniques that will affect multiple units at a single time are necessary. In the paper, we also present a few other key contributions. I encourage you to look at the paper for them. I've listed them here, but we do some validation. We also modify and update Sniper and McPat, as well as 3D-ICE. And we also have a second case study where we scale the entire IC and see what the results of that are using our same techniques. So in conclusion, in this presentation, we've introduced HotGauge, which is a holistic methodology for characterizing hotspots in modern and next generation processors. And I've hoped that through this presentation, you can see how, one, it can quantify the problem in a way that other techniques have yet to be able to do. And two, I hope that you see that if you're in the architecture community and you're aiming to develop architecture level techniques to mitigate hotspots, the HotGauge framework is the perfect tool for doing this sort of analysis in current and future generation processors. Lastly, I just also want to mention that the HotGauge framework is publicly available. It's on GitHub and being updated periodically. And included in this GitHub release is a Docker container that allows you to run all of the thermal simulations and analysis that I've shown here in this presentation, among other things. So that should help you get up and running with the HotGauge framework. And with that, I just want to, on behalf of myself and my collaborators, thank you for your time.